Hello everyone, I'm Xavier Roche, Senior Software Engineer at Algolia, and I'm part of the Engines team, which is a team responsible for maintaining, enhancing and extending the core search and indexing algorithms that we use for all of our products. And today, we're gonna talk about our secret recipe for speed. We'll discuss some of the basic building blocks we have been working on in the last 10 years and how we can build a search engine with them. Algolia has always been focused on speed from the very beginning, whether it is speed of search or speed of indexing. And the reason is that for a single query, millions of hits are scanned and gigabytes of data are involved in the operation. All of that within a 50 milliseconds target. If you take one of the original key features of Algolia, the search as you type, it means that those millions of documents scanned and gigabytes of data are involved for every single key pressed. Now let's have a look at how we sort your data. Because this is a secret for speed. For that, we use extensively modern algorithms, and we build many of the search features on top of that. We wrote our own engine and our own algorithm implementations, mostly in modern C++ with around 200,000 lines of code. That's a lot to maintain and improve, and picking an off-the-shelf solution would have been way simpler for us. But having our own implementation was the only solution to guarantee the performances would match what we wanted to achieve. This foundation powers the Algolia search and indexing engine through libraries or services. Now let's have a look at one of the tightly optimized paths at Algolia, how your data is sorted to be searched fast. For this, we need to index a massive amount of words at large scale. Please note that when we talk about words, it can be anything. Text from records, facet, geolocalization points, or even AI vectors. We'll see that later. But for now, let's keep things simple. For this talk, we'll only deal with small words to explain how it works. One of the basic data structures used to order words are tries. Tries are trees with letters attached to their nodes. Imagine we want to organize words not by storing the whole words at once, but by building them letter by letter. So, for the word cat, we start with a root node C, and then we branch to A, and then we branch again to T. That path spells cat. If we add cab, we don't need to create a new C or a new A. We just reuse the path until it diverges, and then we branch off to B. This way, words that share beginnings like cat or cab overlap in the tree until their letters differ. When you want to look up a word, you simply follow its letters down there. C and then A and then T. If at some point the letter isn't there, you know immediately that the word doesn't exist. It's efficient because the search is step by step through each letters, and you only travel as far as the length of the word. No need to compare it against every word in a list. It also allows more advanced features such as typo tolerance or prefix search. Notice one more time that all those words are sorted. This is a key for speed. Trees or tries are very diverse. They come with different features, and we are using several of them. Another kind of tree is the ternary search tree. This tree has up to 3 child nodes for every node, and the words are only built letter by letter for path going straight down. Otherwise, the letters are here to split the words into 2 parts. The left one with the letters alphabetically lower, and on the right, the one alphabetically greater. The goal of this special tree is to optimize the space consumed internally. It can be more compact, especially with words that are not very frequent. In this example, we can look up the word at. We start with the root node, and on the root node, the first letter is a C, which is not the letter we're looking for. We then go to the left branch, as we're looking for a letter that is alphabetically before C. Then, we find our letter, and we go straight to build the word. The last basic tree structure we want to have a look at is the radix tree. The principle is the same as the trie, except that some parts of the words can be compressed, and a given node may contain several letters. Here again, this special structure can be more efficient in some scenarios, such as when the words are long or don't share parts of them with other words. In this example, see how the word piper has its 2 first letters in separate nodes, but the remaining is compressed in a final node. We gain a lot of space. To have the best of all words, at Algolia, we have been using what we call a hybrid radix tree. This is a mix of tries, ternary search trees, and radix trees we just talked about. We have dedicated algorithms that choose the best option for every branches, depending on the number of words we need to index and their variance with other words, to maximize the speed to find the information we need. And those hybrid radix trees are everywhere. They're used for the regular search, the faceting, to retrieve a record with its object identifier. They're used for synonyms, dictionaries, and rules. They're also used for many natural language processing features. And they're also used for vector search. Now that we can look up words, let's see how we can get the records that match those words. For this, we need another fundamental structure, the inverted list. The inverted list is called an inverted list because, given a word, you can get the list of records that contains this specific word. Again, the words can be anything. Those lists can be very large, and each of them can reference a large part of the records in an index. It's not uncommon to have inverted lists containing millions of records referencing. As an example, the word television can have its own inverted list, providing all the records matching it. This list is sorted. This is important, but you probably know that at this point. Sorting is notably what makes it possible to intersect among different lists. We'll see that later. And this ordering is driven by the ranking formula that was chosen. This order is the same for all lists within an index. Inverted lists are also everywhere. They're used for full-text search, faceting, geolocalization, and AI search, of course. The final boss of our structures is when we mix the hybrid radix trees with inverted lists. This allows not only to quickly find specific words in an index, but also get the sorted list of documents that match them. With all of this, let's build a simple search engine. We already know how to search for a single word. Our mix of hybrid radix trees with inverted list does exactly that. In this example, we have the query television. We first look up the word in our hybrid tree, following the path through existing nodes in the index. Then, on the final leaf, we find an inverted list, the list of documents that contain the word. We then can show the results to the user. But what about, let's say, when we have 3 terms in the query? Well, that's not that complicated. We just need to look up each query terms in our structures, finding the corresponding inverted list. Then we match in parallel all the hits that are present in all 3 sorted lists, scanning millions of records and ranking them in real time. Remember, the first list will contain all the references of the record containing the first query word. But this list needs to be compared to the other list, so that we only keep the records that match all the query terms. In this example, the record 42 will be selected as it's present in all 3 inverted lists. But all of this is not just for text again. It can be used for AI search too. Let's start with a very simple summary of what vector search is all about. We start with some text, and this text is transformed into a list of floating point numbers. Don't worry about their meaning. They represent the concepts behind the text that was transformed, and only the model can understand them. Then, those numbers are transformed again to fit into binary representations of vectors. The final step is to extract the relevant information from the vectors, and the model produces what we call vector signals. Again, don't worry about the meaning of these vectors. This is magic stuff from the model. The only thing you need to understand is that those vectors are also words, and we can index words in our data structures. And because of this, we can be efficient and have the same speed for indexing AI vectors than the speed we already have for other features. And with this, we can build our basic AI search with an intermediary step. If we take the query Philips Television 32, the model will provide a number of vectors. These numbers vary depending on the model. Again, at this point, this is magic. Once we have all these vectors, we just match them as we would for a full-text search, only keeping relevant records. All of this was a very simplified view, but we hope it allowed you to grasp what was going on behind the scenes. So, what did we learn? We learned how to index words, or facets, AI vectors, and so forth. We learned how to retrieve documents matching them. And we built a very simplified AI search engine. The takeaway is that sorting data is the key for speed. And developing advanced algorithms is critical for the future, as it allows for later advanced uses such as personalization, re-ranking, and so forth, up to AI search. Those are the building blocks that have been used for the past years, and they are still relevant today, even in a world where AI search is changing the face of Algolia. If you want to know more about the Algolia engine internals, you may want to have a look at the blog of Julien Lemoine, the founder of Algolia, by searching for Inside the Algolia engine on a search engine, or simply scan the QR code on the screen. You'll find absolutely fascinating details on many of the other algorithms we are still using to power our search. Thank you.